So let me see how many people. 128. So one announcement, many people are not interacting in class. So, and suggested means and students are suggesting for doubt clearing class. So, which is completely what you can say paradox. People are attending classes but not clearing any doubt, not asking any questions, and requesting for doubt clearing class. And after the class, once the class finishes, so what happens? Many people, so they don't log out. That means they are not at all listening or doing anything. So they simply log into the class, and after end of the class, I generally means forcefully remove many students after the class. So please be attentive. So today we'll move towards a new topic, that is scheduling, and it will be the pre-topic for cloud computing, HPC, and what you can say edge computing and fog computing. So before going to the cloud computing sites, so we'll start with the basic scheduling mechanisms. Okay, so in OS course, what kind of scheduling you have read?
Sir, round robin, priority based, and the shortest job first.
Only these three, no other.
No, sir, and a
Skip,
combination
sir.
of them.
Preemptive version
Uh,
also.
Preemptive version.
Yeah, first come, first serve.
First come first serve.
Shortest remaining time.
Shortest remaining time.
The largest remaining time first.
Okay, that's fine.
And
So
sir,
in your so in your
and
algorithm book, what kind of scheduling algorithm you have read? Algorithm course.
The job scheduling.
Farthest
in future.
Hmm?
Farthest in future.
I'm not getting. Only 1%, please tell.
Farthest in future first.
Fastest and
Farthest in future first.
farther and future scheduling. Okay. So now, so this whatever you have read in your scheduling chapter of your OS book or in your algorithm book, so that will be extended to maybe 5 to 10 lectures or maybe whole rest of the course. Okay, so think of only scheduling. So it will try to solve scheduling problem related to cloud, related to IoT, related to fog computing, okay, related to edge computing. So everything we'll try to focus on scheduling problem now.
Sir, what exactly will you be learning in cloud?
So particularly cloud economic model, cloud resource management, and in cloud resource management we'll mostly focus on scheduling, related to scheduling, how we can manage the clouds very nicely. Okay, so particularly not from the programming point of view, from the management point of view. Suppose you are a cloud provider, so how you will do that thing? Okay, so let's start
yes,
with the
sir.
let's start with the scheduling concepts. Okay, then we'll move towards the initially we require very good ground, or what can say basic material of scheduling. Then only we'll move towards the cloud. Okay, so cloud, IoT, and edge. Okay, so let me say the slides. So or before that, let's discuss something. Uh, in what is the SGF settling? So you have read about SGF settling. So how it is better?
Shortest job first. So
Yeah.
So it has the best
we
throughput.
have to calculate first the burst time of each job, and then we have to schedule it accordingly. That which job has the smallest burst time, we schedule it first.
Okay, but what it do? What is how it do? That it depends. My question
It
is what it.
reduces the waiting time.
it reduces waiting time for shorter jobs, which otherwise would have like waited in queue after long jobs for a long time.
No. My question, you try to answer me algorithmically. So suppose n taxes are there. Okay, n taxes time zero.
It will prevent starvation of the shorter jobs. Like if a very large job enters the queue.
No. So let me do. So let me answer the question or refine the questions one more time. So suppose there are n taxes. Okay, arrived at time zero, and you have one processor. Suppose you have n taxes with execution time is given. Okay, and only you have one processor. Okay, and your main aim is to minimize the overall waiting time. Can I say that shortest job first scheduling will definitely give you the optimal result?
No.
No, sir.
So in that way, I'm saying.
Sir,
Okay.
it gives if all the
Yes, sir,
jobs arrive at same time, then it is the minimum.
Yeah. So in that way, I'm saying. So it minimize the waiting time. It minimize the waiting time. Suppose it all job don't arrive at zero time, then preemptive version of SGF, shortest job first, will give you the optimal thing. Okay, so that optimality means particularly given a problem, suppose we want to solve optimally, algorithmically. So in this course, so we'll try to think in the similar line. So how algorithmic scheduling problem get defined, how the scheduling problem gets solved, okay, and what are the scheduling problem is still means unsolved means which are the scheduling problem which map to actually NP complete problem, which kind of scheduling problem can be solved in polynomial time. That thing we'll discuss now, means from this class onwards. So now it is not programming, now it is pen paper based. Okay, so let's start with our theoretical part of cloud computing or HPC. Yes. So let me share my screen. Hope my screen is visible. So let's start with the stack scheduling part. And in this class, we'll try to discuss about the scheduling concepts, particularly very basic of scheduling concepts. And then we'll look at independent tasks and dependent tasks. Independent tasks means they don't have dependency among tasks that can be executed in parallel. And dependent tasks means one task will depend on its predecessor or successor. Means it suppose a task will have a predecessor, then it will depend upon predecessor. And after this execution a task, it's all successor tasks can execute. So that is dependent tasks. Okay. And for this whole means what I can say scheduling related thing. So mostly we'll refer this book, Scheduling Problems. So there is a book called Scheduling Algorithm by Peter Brooker. And this book, if you Google it, then you'll get this Google scheduling algorithm Brooker PDF. You'll get the PDF copy of the book, and definitely I'll upload the soft copy of the book to the MS team. So if you simple Google scheduling algorithm Brooker PDF, you'll get the PDF copy of the book. Okay, and definitely this will be uploaded to the MS team. And these are the three terminology. So suppose given a set of n tasks, need to execute. Okay, so what I'm saying is, so given n tasks need to execute. Okay, so goal may be time, power, energy, but I'm not saying what is the goal. Okay, so what to minimize or what to optimize or what to maximize, I'm not saying. But what I'm saying is very basically given n tasks to execute. And for example, n means suppose n is equal to 10 taxes, and A, B, C, D, E, F, G, H, I. There are this named 10 taxes. And there are three things comes whenever any scheduling problems or if you see from the problem solving point of view, one thing is allocations. Okay, to execute the n taxes, how many compute unit or how many processor, what type of processor you require? That is called how many compute unit or how many processor we require. So that is called allocations. First thing is for executing this n taxes, we are allocating suppose 3 processor or 4 processor or 2 processor of this type and 1 processor another type, or 1 processor of this type and 1 processor another type. Okay, so first things come is allocations. Allocations means it tell about the number. It tell about the number. Second one, it comes with binding. So where to execute? Okay, so which tax on which processor? It tells about which tax on which processor. Okay, so clearly what it says, so in this example case 10 taxes, suppose if you say example 3 processor, then binding says which tax will go onto which processor. Okay, that is binding. That means in this case, in this example, what I am saying is, so this A, C, and F, it goes to processor 1. D, E, H, and I, it goes to processor 2. And B, J, G, it goes to processor 3. So this is one example. Okay. And 10 taxes, 3 processor. And this is the division. And then third point comes, is called scheduling. Scheduling when to execute. At what time the task execute on the binded processor. So first one is allocations, it tell about number. Second thing is it tell about the space where to execute. Okay. And third term, particularly settling, it says when to execute. When to execute. Okay. So at what time the task execute on the binded process. Have you heard about the Gantt chart in OS course? We have read this thing Gantt chart.
Yes, sir.
Yes, sir.
Yeah, Gantt chart, it display. So suppose you have only one processor, then allocation and binding will not make any sense. Suppose you have one processor. So assume that you have one processor, that number is defined. Then binding means all tasks will execute on one processor. But whenever the number of processor increases, okay, and however from the pool you need to get the number of processor, then this allocations, binding, and settling come into picture.
Sir, I have a doubt.
Yeah.
While scheduling on multiprocessors, once a process is assigned to a processor, is it not changed? I mean, dynamically.
It can change dynamically.
So
Dynamic scheduling. If it is dynamic scheduling, then that assignment can be changed. That means whenever you say binding is static binding or dynamic binding. So in this case, so if I give you an example, this is a static binding.
yes, that is what I wanted to ask. Static binding is very hard because
that is static binding. And another thing is scheduling also you can define as dynamic scheduling or static scheduling. Okay. So static also you can define the at what time it will execute, or dynamically also you can say at what time it will execute. So there are 3 variations: dynamic allocations, static allocations, dynamic binding, static scheduling, and dynamic scheduling. So all the things will come. So, but basically what I'm trying to say is what is allocations, what is binding, and what is scheduling. But variety may come second. Okay. It is clear?
yes, sir.
This is the starting point of our whole course, rest of the course. So you should be able to understand clearly. Otherwise, you will not be able to understand any further lecture.
Sir, when we say allocation, it's basically mean in terms of cloud only, that we have a large number of processors and hardware.
So it may not be. Not only means in terms of cloud. So this is generalized scheduling problem. Or given any n taxes to execute, or we want to run n taxes, on how many processor we want to run? How many we got allocated? So this is allocations. Suppose you have you want to hire something, okay, and how many you are hiring? So based on you define. Suppose you want to run a conference, and there will be many communications of guest and your things. suppose you want to hire 3 car. So that number is 3. You got allocated 3 number. But who will do where, how will transfer that binding later on you can decide, or scheduling later on you decide. But allocation is must tell about the number.
Okay, sir.
Okay. And one thing is number, binding is tell about the space. Space can be dynamically or statically. Okay. So if you are deciding statically, then before executions it's decided clearly, and it is dynamically, then this who will go to which task will get into which process, that also get decided dynamically. That means dynamic binding we are doing. Okay. So many times this people get confused with allocations and scheduling. Okay. Binding no wonder, but whenever it's allocation and scheduling. So in dynamic case, allocation and scheduling, they do means what I can say not interchangeably, they use this term allocation and scheduling. So many times we see that scheduling tasks onto processor or allocation tasks onto processor, they interchange this term. But if you look at from the top, then it have actually clearly 3 different distinctions. Allocation means it tell about the number, binding it tell about the place, and scheduling it tell about the means at what time it executes.
Sir, what is the typical sequence of binding and scheduling? Do we do binding before scheduling, or we do scheduling before binding?
So that also we can define. So some algorithm they do before scheduling, scheduling and binding do means what I can say one after another, and iteratively also they refine the scheduling and binding. So some algorithms, so they combine scheduling and binding also. Okay, so we'll see means this thing when other things proceeds. Okay, is clear?
Yes, sir.
Yes, sir.
Yes, sir.
So scheduling problem. So we look at find time slot in which activity or job should be processed under a given constant. So if you look at any given problem, so scheduling problem in general we define find time slot in which the activity or job should be processed under a given constant. And what is the constant? So constant is resource constant or precedence constant between the activity. So earlier it was actually what I say is very high level, this common terminology case, but now we are reducing to a resource constant project scheduling problem. So take any almost all scheduling problem, it actually termed as resource constant project scheduling problem, and it is a quite general scheduling problem. Okay, so what are the constant? Resource constant. Second one is precedence constant between activities. Suppose you are taking not independent job but dependent job, then predecessor and successor kind of things. It unless the predecessor execute, you cannot run the task. Okay, so this is precedence constant, and resource constant come from the allocation side. What are the resources? How many resources? Okay, so and looking at the point things, so find the time slot in which the activity or job should be processed under the given constant, the resource constant and precedence constant. This is the standard definition of scheduling problem. Okay, and this problem, initially this scheduling problem is from actually not from only CS or mathematics. So this scheduling problem is start with actually mechanical engineering and civil engineering scheduling problem. Okay, so they have manpower, they have machines, how to schedule the machines. Suppose you are using the same problem in actually car manufacturing or industrial manufacturing, how to schedule the jobs, how to schedule the activities, so that it will be done means with some optimizing the things. It is a more a generic problem. So one of the book, so whatever we are referring, this Peter Drucker, he's a mathematician and computer science guy. But there is another good book that is called Michael Pinedo. So he's a mechanical guy, production engineering guy. Okay, so he also wrote a very nice book on scheduling problem. Okay, so this is not only related to only CS guys, but it is a very more generic common problem. So what is resource constant project scheduling problem. So
Sir,
we have suppose many activity. So 1 to n with processing time pj. Okay, so we can say n jobs. Okay, with processing time pj each job. There are resources, k resources, k is equal to 1 to r resources k, and a constant amount of rk unit of resource k is available at any time. Okay, so that means what I can say, a constant amount of rk unit of resources, rk unit of resource k is available at any time. That means what I can say, rk means every resources have actually some compute capability or something. Okay, and during processing, activity j occupies rjk unit of resources. Okay, so suppose you process the activity or job on kth resources, then it will occupy rjk amount of resources of resource k. Okay, so it's kind of means suppose n jobs and suppose 5 processor are there. Okay, n jobs and m processor. So in general, in our domain, what we will do look at is n job and m processor. Okay, n job and m processor. Okay, n is in generally will use for number of jobs. M will generally use for number of processor. Okay, and during the processing, the activity or job j occupies rjk unit of resources. That means what is the CPU utilizations in terms of that CPU utilization. Suppose CPU utilizations is 0 to 1, then how much CPU utilizations it will take. Okay, so in that also you can correlate and do. And this is precedence constant is I2j means some activity ij with the meaning that activity j cannot start before I is finished. So in terms of DAG, directed acyclic graph, or directed graph, suppose you are taking directed acyclic, that you can do that thing. Not the directed graph, but directed acyclic graph. If it is cycle, then we cannot define the predecessor and successor. Okay, so it need to be directed acyclic graph, then only we can define. Is this fine? So why I'm saying only direct, not DAG, not simple directed. If it is only directed and it have cycle, then you cannot define the predecessor successor relations. But if it is directed and acyclic, then we can define predecessor successor relations for a node. Okay, how many predecessor and how many successor. And for DAG, directed acyclic graph, what sorting algorithm we use in your algorithm course?
Topological sort.
Topological sort.
Yeah. So given a DAG, we can run topological sort on the DAG. Okay, so all the nodes can be ordered from 0 to n. Okay, suppose n nodes DAG, it can be ordered from 0 to 1 to n in a topological order. Okay, so one after another relations. Okay, only for DAG we can do. If it content cycle, then you cannot do. Okay. And objective. So objective can be determined on the start time Sj for all activity j in a such a way that so at each time t, total demand of resource k is not greater than availability of rk. Okay, so that means this is a constant. Okay, and given the precedence constant are fulfilled. So what is the precedence constant? So suppose j is a successor of I is predecessor of j. Then what will happen? So this relations. So start time of j. Okay, Sj, start time of j should be greater than starting time of ith task plus processing time of I. Okay, so in that way, other way around. So Si plus Pi should be less than equal to Sj. That means after finishing the ith task, then only we can start the jth task. This is it need to maintain the precedence constant, and first one is resource constant. Okay, and son, whenever we say objective is, first thing is we want to determine the starting time of all the activity. Okay, given the constant. These are the constant. Okay. So what is the one? First one is resource constant. At each time t, the total demand of resource k is not greater than the availability of Rk. This is the resource constant. That means, suppose in case of our regular CPU scheduling case, so CPU means what I can say usage should not exceed more than 1. Suppose in CPU resource in general you calculate from 0 to 1. Okay, so in that case it need to be less than equal to 1. And if it is a DAG, then the given the precedence constraint need to be fulfilled. This is what we are saying. We are trying to determine the start time of all the tasks given the resource constraint limit and precedence constraint limit. This is from the what point of view? So this is point of view. We want to execute all the tasks within the resource constraint with maintaining the precedence constraint. But on top of that, there may be many solutions. Okay, so there may be many solutions, and some objective functions is minimize. Suppose a function of f c1 to cn, which is minimized where cj is the sj plus pj is the sj plus cj. So cj is what I am saying is completion time. Okay, cj is completion time. Function of c1 to cn means function of all completion time. Okay, minimize is minimize. Suppose you want to minimize completion time of all the tasks, then what you will get? Overall execution time we are minimizing. Okay, so suppose you want to minimize completion time of all the tasks, then you are minimizing overall execution time. Okay, so the fact that activity j start after time sj and finishes at time sj plus pj implies that activity j are not preempted. Okay, so in this case, this implies that activity j are not preempted. Okay, so that means whenever I am saying sj plus pj, that means this applies activity j is not preempted. And if you want to relax these things, we may relax these conditions by allowing preemptions, activity splitting. So that can be done with a different way. So we can correlate this problem to our regular problem. Okay, so this is a resource constant project scheduling problem. Okay, so this is very simplistic example. So consider a project with n is equal to 4 and r is equal to 2. How many resources? Resources 2. And resources with capacity, R1 have capacity 5, R2 have capacity 7. And there is a precedence relations 2 to 3. Okay, so this is the ith 1, 2, 3, 4, and this is the PI. So this is what is PI? PI is the execution time of this task. Okay, and this is RI1 and RI2. Okay, so what is RI1? So whenever you execute this process, it will take this many resources, 2 resources of 1 and 3 resources of 3. Okay, so whenever you execute, so is this fine?
Sir, what is RI1 and RI2 here?
So it will take 2 resources of R1, okay, and 3 resources of R2. So this is suppose this is P1. Whenever I say P1, so P1, this is task 1. So task 1, 2 resources of, are able to see this this block? It takes 2 resources of R1, resource 1, and in this case 2 resources of 3 resources of resource 2. It's taking 3 resources. For durations, 4 time unit durations. This is the durations. This is the durations. This is the duration. This RI1 and RI2 is signifies. So to execute the task, P1 means first task, 1 task, it requires 4 unit times, and at that time we require 2 resources from R1 and 3 resources from R2. Resources capability. Okay, so kind of things that suppose there are means very roughly I can say to do my suppose you want to this kind of work. So at a time we require suppose 2 plumber are require and 3 electrician we require, and we require for 3 days. Are you getting a point? Suppose you are doing some building work, okay, and 2 plumber and 3 electrician for how many days? In that way, you just count. So this signifies, so one is plumber and other is electrician, and this is for how many days?
Okay, sir.
And
So for each resource and for each process, there is a corresponding time that process requires that resource, right?
no, this is PI is given. So this PI says that. So tax one. Suppose tax one is this says that I require for 4 days 2 plumber and 3 electricians. For tax 2, I require for 3 days 1 plumber and 5 electrician. Are you getting a point?
Okay, so in the rows there are resources and columns there are processes, right?
Yeah.
Okay, fine. Sir, one more doubt. While using resources, can a single process utilize many resources simultaneously?
Now, in this case, it is individual. So, in this case, resource, what is the capacity is given? Suppose if you divide into smaller chunks, suppose if your processor have 0 to 1 capability and divide into means 25%, 25%, 25%. At a time, we can give 25% together. Means it is not unit is 25% of resources. That means this whole processing capability divided into 4 chunks, and this 4th chunk you cannot divide lesser than that. Suppose then it can be considered as capacity 4 with 25% usage. That also can be done. Okay, but not in this case. What are the basic? This is all what I can say integer example to make you understand.
Okay, sir.
What is given is integer example so that you can make understands. Okay, and this chart it shows it is a what is this? This is Gantt chart. This is a little bit more complex one, but it is a Gantt chart. Okay, so if you look at a process means job 4, it require 8 unit time. Okay, and 8 unit time, 2 plumber and 4 electrician. This is 2 plumber and this is 4 electricians for 8 days. Okay, so in that way.
Hello, hello.
Yeah. Hello, I'm not able to listen to your questions.
Hello,
It's not audible. I'm not able to listen to your question.
Sir, can you hear me? Hello.
Yeah, now I'm able to hear you.
Sir, my question was, so in this example, the process requires 2 plumbers and 4 electricians, both at the same time for 8 units of time. Is that correct?
Yeah, that's correct.
Okay. So for continuously for 8 units of time, it requires them simultaneously.
Yeah.
2 plumbers and 4. Okay.
And this right side diagram is called, actually this is Gantt chart. Okay, so in your OS book it is actually a very simplistic thing one, but nowadays looks very complex, but still it is a Gantt chart only. So at what time how many resources get used from which resource pool for which taxes. Okay, so exactly same thing. And in this case, what we are trying to do is 2 is actually predecessor of 3. So if you look at 2 and 3, one after executing 2, we are executing 3. Okay, in these examples. And it is taking time 12 minutes. Okay, so ultimately in this case we are trying to minimize the max1, and it given this kind of scenario, so this is taking 12-minute time. And application of the scheduling, so mostly it is for production scheduling, robotic cell scheduling, computer process scheduling, timetabling, personal scheduling, railway scheduling, air traffic control. The scheduling is more common problem. It get used everywhere, almost all the places, almost all the science they use actually scheduling problem. And what we are trying to look at from the computer process scheduling point of view. Okay, but this previous resource constant project planning problem. So this is actually more common. Okay, resource constant project scheduling problem, PSP. This is RCPSP. This is actually what I can say more generic one. Okay, and this is common scheduling problem. And this machine scheduling problem and their classifications. Most of the machine scheduling problem are specialized. Special case of this resource constant project scheduling problem. And in our OS book, we have read single machine scheduling problem, online problem. Okay, so FCFS, SGF, SRF, round robin. So the all are means you have already read in your OS book. Now we'll look at what is parallel machine problem, what is sub scheduling problem. But in general, we'll look at only single machine problem and parallel machine problem, not the sub scheduling problem and multi machine problem. That will not look at. Okay. Suppose single machine problem. So that we have already studied this thing in the OS course, but this is we are trying to look at from the RCPSP point of view. So have suppose just 1 minute.
सर आपका ये दो हार्ड कॉपी आपका मेल बॉक्स में आने लग गया सर उस टाइम
यहाँ पे साइन करने दे
हाँ सर
Sorry for disturbance. Someone came and knocked my door and took signature. So this is the demerit of online classes. Okay, so in classroom, no one disturb. So suppose you have n jobs, okay, 1 to n, and process on a single machines, and additionally precedence constants within jobs may be given, and the problem can be modeled as this RCPSP, and where R is equal to 1, okay, and R1 is equal to 1, and RJ1 is equal to 1 for all the jobs. Okay, because number of resources R is equal to 1, R1 is equal to 1. So we have only one processor in that resources, and RJ1 is equal to 1 for all the jobs. So all job assigned to only one processor. Okay, so this is a single machine problem. Whenever you say parallel machine problem, so P, we have job J as before, M, suppose M identical machines. So there are, whenever you define these things, there are many cases comes. Okay, so identical machines, suppose M1 to MM. So whenever I say n jobs, so n is we generally represent for jobs, and m is for machines, number of machines, and processing time for j is same for each machines. So whenever I say identical machines, okay, whenever I say identical machines, the processing time for job j is same on each machines. Okay, so all are homogeneous machines. We can say homogeneous when I say or identical whenever say, that is processing time for j is same on each machines, and one has to assign job to the machines to schedule them on the assigned machines, and this problem is correspond to the same specialized version of RCPSP with R is equal to 1. Okay, R is equal to 1, R1 is equal to M. So how many machines? How many type of resources? Is R is equal to 1, R1 is equal to M, and again RJ1 is equal to 1 for all the jobs. It will be assigned to R is equal to 1. How many resources? Because M number of machines are there. Okay, so identical machines. So with R is equal to 1. Okay, in that way we are saying. Okay, and R1 have M machine.
Excuse me.
J is equal to. So in this case, earlier case we had actually plumber or electricians, and in this case we don't have plumber electricians. All are electricians or all are plumber. So this resource type R is equal to 1. Is this clear?
Sir, by a resource, do we mean a processor?
Yeah, resource means processor, we can assume. But whenever you are saying resource constraint project scheduling problem, the resources may be of different type.
So via resources, like each machine is a resource. That's what we are considering.
But all are machines.
So one machine is one resource. That's what we are considering, right?
Look at how many number of machines. If R is equal to 1 represent how means machine. Suppose machine and another resource is printer. Then we can say there are two kind of resources, machine and printer. And how many machines were? We have M machine.
Oh, okay, got it. Sir.
So
Yes, sir.
in earlier example, what I say is plumber and electrician. So now only one type of means of resources, either plumber or electrician. So in this case, what I'm saying is only machines. Okay.
Yes, sir. Yes. Thank you.
So this is parallel machine problem. So this is a very simplistic examples. So left side one is this is a DAG. Okay. So directed acyclic graph. So and these are two component. Okay. So still it is acyclic one, and this need to assign to how many processor? 3 processor, M1, M2, and M3. And this some way we have assigned this thing. So this is one is executing. After that, 2, 3, 4 are executing. This is maintaining the after execution of 1, then only 2, 3, 4 are settling, and after 2, 3, and 4 get executed. 2, 3, and 4 get executed. Then 5 is got scheduled, and after means you can say 6 can be executed in, but before means after execution 6, 7 gets scheduled. Okay, and after execution of 2, 8 got scheduled. After execution of 2, 8 got scheduled. And where you are getting what is the Cmax time? Cmax means what is the maximum? What is the time we are taking here? It's 9. So we generally minimize the Cmax. Okay. Maximum time is 9. We want to minimize that maximum time taken. Okay. So in general, most of the problem, suppose you want to minimize the overall execution time, then minimize this part. Okay. So minimize the rightmost part. So this one. So parallel machine problem, if you look at, so we have P. So already we have defined for P. So where we have J jobs and have identical machines. Okay. So now we are terming another term Q. The machines are called uniform if Pjk is equal to Pj by Rk. That means all are similar machines. Okay, identical machines, but with different speed. All are different machines. Okay, similar machine but with different speed. They are different in terms of speed. Okay, so this is uniform machines. And third kind of machines are processing is called unrelated processing. Okay, R. Unrelated processing is the processing time Pjk depend on the machine Mk, on which machine J is processed. And a last kind of thing is MPM, a problem with multi-purpose machines. Set of machines mu J is associated with this job, indicating that J can be processed on one machine in mu J only. So this thing we'll not consider now, but we'll look at PQR. So with example, so that we'll be able to understand very nicely. So our brain get tuned whenever we think in terms of examples, but it may not be. Okay. But let's see. So what is the example? Suppose there are 4 taxes and 4 machines. So taxes are T1, T2, T3, T4, and machines are P1, P2, P3, and P4. Suppose in identical case, what will happen? So identical what happening? So T1, wherever you executes, this execution time is same. T2, wherever you executes, the P1, P2, P3 or P4, its execution time is same. Similarly for T3 and T4, this is identical machines. And whenever say uniform, so whenever I say uniform, so it is machines are same, but they are different in terms of speed. Suppose T1, suppose this is machine 1, suppose P1 processor 1, so these are tasks T1, T2, T3, T4. So T1 executes on suppose P1 10 times. Then whenever you execute on P2, the execution time depends on the speed of the P2. They are identical, but they are different in terms of speed. Okay, so in this case, speed of S1 is equal to 1, speed of S2 is equal to 2 by 3, speed of S3 is equal to 1 by 2, and speed of S4 is equal to 2 by 5. Suppose this is the example. Suppose, and based on speed, the execution time will get reflected. So T1 here it is taking 10 times. So if you run on P4, so it will take 25 minutes of time. Okay, so what is the speed? So 10 by speed. Okay, so 10 divided by speed. If it 10 by S4, if you, what will be the result? So 10 by S4. So let me change to what I can say pen. So suppose what I do, suppose I want to execute T1, this T1 on P4. Then what will be execution time? So 10 divided by S4. What is the S4? 10 divided by 2 is 5. So 10 into 5 by 2. So it will be 25. So these taxes, okay, so T1, T2, T3 and T4. If you execute on P1, then 10, 12, 16 and 20. So if you execute on P2, then it will be proportionally execution time will increase. So 2 by 3 time. So but that means speed is 2 by 3, and how much increase in execution time? It will be 3 by 2. Okay, so 1.5 guna ho jayega. So 1.5 time. So 10 to increase to 15, 12 increase to 18, 16 into 24, and 20 increase to 30. So similarly, P3 speed is half. Speed is half means execution time will double. Okay, so this is the example. And another thing is unrelated. Unrelated means there is no correlations. So identical means, so given a task, wherever you execute, execution time is same. Uniform means execution time depend upon speed of processor. And third one is completely unrelated. Is R and is heterogeneous. All machines are different type and configuration and all the things. So we cannot say how much time it will take. First one is homogeneous processor. Second one is homogeneous processor with different speed. Fourth one is completely unrelated. Okay. So is this clear? P, Q, and R. Hello.
Yes,
P,
sir.
Q, and R.
Yes, sir.
P is identical, Q is uniform, and R is completely unrelated, heterogeneous.
So why is Q uniform?
Hmm?
Why
No,
is the second one?
second one is whenever you define any problem, so what kind of actually machines we want. Okay, so Q stands for uniform machines, and uniform machine means it identical with speed difference. So mathematically, we define this nomenclature. Mathematically, we are defining the nomenclature. This is the how we're dividing the class of machines. Okay. And whenever say R unrelated means it is completely heterogeneous. Which taxes will take how much time on this thing is completely unrelated. Okay. So first one is completely related. Second one is equal. Second one is related with speed, and third one is unrelated. Okay. So in that way you see. And take any classification problem. So classes of scheduling problem can be specified in terms of three field of classifications. First, alpha, beta, gamma, this is the notions. And where alpha specify machine environment, beta specifies job characteristics, gamma specifies the objective functions. Okay, so let's look at this thing from the example. Okay, so but this first thing is alpha, is machine environment. Second one is job environment. Third one is the objective functions. If I say suppose n taxes arrived at time 0 and there are one processor, all taxes are independent, and we want to minimize the overall waiting time, sum of waiting time of all the taxes, overall waiting time. Then can you write these things? So alpha is machine environment is one machine. Okay, that is P1 we say. Okay, or 1. Beta is independent, non-preemptive. Okay, so independent, non-preemptive. And third one, what we are minimizing? Minimizing the summation of completion time. Summation of completion time. Okay, or
starting time, because waiting time we are.
yeah, that also starting time will actually get reflected to this. So that we'll see. Okay, so how we can the summation of completion time will same as actually average waiting time or average what I can say average waiting time. That we'll see. Okay. So when we come to example, then we'll see. Okay, so this is machine environment. What is the symbol meanings? So one means single machines. P means parallel identical machines. That parallel identical machines already we have defined. Okay. Parallel identical machines already we have defined. Okay. What is uniform machine also we are defining. So these uniform machines have different speed, and R is unrelated machines. Okay. And this multi-purpose machine, job scheduling, flows of that we are not going to discuss in this course. Okay, so we'll consider only first four. 1, P, Q, and R. Okay, if the number of machine is fixed, then we write M, just like PM, QM, RM kind of things. If number of machine is not fixed, then we say it is general machines. So suppose you design a algorithm, so which will schedule the jobs if number of machine is fixed, for a small number of machines. Not generic, not arbitrary, but small number of machines. If number of machine is fixed, then very small, and then we write PM, QM, and RM. So that also will distinguish. Okay. So whenever this suppose number of machines is always less than 10, then you can design algorithms to solve your scheduling problem, which may be exponential to this 10. Still, it is fine. But this number of machine is very high. Then you cannot design a exponential algorithm which is some p to the power m or something to the power m. But if it's this m is very small, then you can design. Job characteristics. So many times we have asked, so whether we allow preemption or not, whether job has release time or not, whether job has deadline or not. Okay, so whether job have execution time is unit execution time or fixed execution time, or it is means arbitrary execution time, or the execution time is from the set, some set, fixed set. Okay, so that also job characteristics. Whether precedence constraint is there or means how it is there, and then whether it is this precedence constraint is in tree or out tree. Tree is means a specialized version of what I can say precedence constraint. Can I say tree? Means suppose what I can say directed acyclic graph and tree. Both are directed, but tree is means much simpler as compared to DAG. Can I say this thing?
Yes, sir.
Because we have number of connection is less, and another thing is there is no multiple paths in tree. Only one path exists, and in tree always you can maintain either it is a in tree or out tree. We can say it is a either in rotate or out rotate because it is a tree. Okay, And another thing is chain dependence. Chain dependence means every tractor have either one predecessor or one successor, not more than that. There is chain. And series parallel. So is series parallel precedence graph. So let me show you graph whether I have this graph or not. I don't know. Okay, so I don't have. So in next classes we will see example of all the things. Okay. And optimization functions. So last one is optimization functions. So two type of objective functions are most common. One is bottleneck objective functions. Okay, so max of FJCJ. Okay, so if I say means we want to minimize the overall execution time. Suppose CJ is completion time of task as J. Then how will say max FJCJ function of CJ. Okay, so suppose minimize the means completion time of means what is the what you can say overall execution. Suppose you want to minimize. Okay, suppose what I am saying is Cmax. Cmax. So suppose completion time of all taxes is C1, C2 up to Cn. Suppose this is the completion time of all taxes C1, C2, Cn, and you take the maximum of completion time, and we want to minimize this value, minimize Cmax. Can I say I am minimizing the overall execution time? Yes. So overall execution time, if you minimize, then it will minimize the Cmax. Suppose Cmax is the maximum of C1, C2 up to Cn. Okay, so there are two kind of functions. Either one is bottleneck functions, other one is summation functions. Some objective functions, so which is summation of FJCJ, and which can be F1 of C1, F1 of C2, and so Fn of Cn. So it is actually, can I say, suppose how much time I have? 57. 1 minute I can discuss. Okay. Suppose n taxes are there. Suppose n taxes, all tasks arrived at time 0, and each taxes are processing time P1. Okay. P1, P2, P3, and Pn. So this is the execution time. All tasks arrived at time 0. That means release time is equal to 0. So all tasks arrived at time 0. And suppose you have only one processor. Okay. So I am say P1. So this is 1. And I want to execute these tasks so that overall waiting time is minimized. Overall waiting time is minimized. So you know this algorithm. What is this algorithm?
Shortest job first.
Shortest job first. Suppose preemption is not allowed. Shortest job first. Okay, SJF is optimal. So SJF optimal. What we are optimizing? So we are optimizing waiting time. Suppose we are optimizing the suppose. So these are completion time C1, C2 up to Cn. This is the completion time. Suppose this is completion time of this thing. Suppose we want to minimize. Suppose C1 plus C2 plus Cn. If we minimize this, if we minimize this thing, so suppose 1, then this, and what are the things? Independent taxes. This is independent PI, and all arrived at time 0, and no preemptions, no PTMN. Preemption is not allowed. So machine environment is 1. This is the tax environment, and this is what we want to optimize, minimize C1 plus C2 plus Cn. Okay, this is kind of minimize summation of Ci. Is this fine? If we minimize summation of Ci, can I say it minimize waiting time?
Yes, sir.
So what waiting time is? What waiting time is?
The time each process takes to complete is fixed, right? So if I remove that constant part, what I'm left with is only waiting time.
Waiting time. So all completion time. So if you look at completion time is waiting time plus processing time. Can I say?
Yes, sir.
Yes, sir.
Pi is equal to waiting time plus Pi. Anyhow, processing time, if you sum all the things, then what will happen? So C1 plus C2 plus Cn, if you do these things, so W1 plus W2 up to Wn plus P1 plus P2 up to Pn. So anyhow, we cannot minimize this thing. Anyhow, this is the processing time. Only thing is waiting time need to be minimized. If you minimize this waiting time, that means it is same as minimizing C1 plus C2 plus Cn. Is this clear?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah. And this is the problem statement. What we are trying to say is we are trying to formally state the problem of minimizing waiting time of n tasks on one processor with no preemptions. So how we can write this thing? So this is 1, then this is alpha, beta, and this is gamma. Gamma is equal to, so minimization of summation of Ci. Okay, or directly we simply remove this in summation of Ci we write, and this is, we say Pi, Ri is equal to 0, no PTMN. So this is the task environment, and this is the machine environment, this is task environment, and this is the objective functions. So any scheduling problem can be represented using alpha, beta, gamma notations. Okay, so alpha, beta, gamma notations. Is this clear? And with
Sir,
this,
could you explain what is RI? What is RI?
So in this case, Ri is release time, I am saying, so not the resource one. This is release time. Release time is all job arrived at time 0.
Okay.
Okay, so all job arrived at time 0.
Thank you, sir.
Any questions? Now everything will be pen and paper, so we'll not write any program. Okay, so you need to understand very clearly.
Sir, also in these cases, deadlines are infinite,
Deadline are infinite. So whenever we don't mention deadline, then by default it is infinite. So there is no deadline. Okay. If you have any questions?
Sir, whenever we say identical machine or uniform machine or unrelated, we always mean that there is only one machine type.
No. One machine type we are saying, na?
Yes.
Yeah, that is one machine type.
Okay.
So identical means one machine type, and uniform means machine have one machine type but different speed. But whenever we say R means unrelated, then machine are of different type, you can say. But that numbers is defined.
Sir, for gamma to minimum, can we say that shortest job first is solution?
Which one?
Scheduling, shortest job first schedule.
So whatever we define problem, so that how we can define problem using alpha, beta, gamma format. And I gave example of this problem. And that problem can be solved using shortest job path, not all the problem. For that problem, it can be solved. Okay, that is the one problem, very simplistic one problem can be solved using shortest job path. Okay, and that is for one machines. Okay. Okay, thank you. So if you don't have questions, then you can stop the class.